Hello everyone, welcome to today's webinar, Digital Workflow for 3D Printed Insoles from Ideal to a High Value Product. My name is Yvonne Lim, Business Development Manager with EOS APAC team. I will be your facilitator for today's webinar. We will start the webinar in a few minutes' time as we allow more participants to dial in. In the meantime, let's familiarize ourselves with the communication functions of this platform. Please be informed that this webinar will be recorded and all lines will remain muted during the webinar. Feel free to type your questions in the question box as shown in the control panel on the top right corner of your screen. We will answer all your questions via a chat or at the end of the webinar during the Q&A session. In addition, at the end of the webinar, we hope that you can give us your feedback via a short survey so that we can continuously improve our content to meet your requirements. In today's webinar, we have gathered leading experts from 3 companies, EOS, Materialise, and DyeMansion, to share with you how it's possible to quickly realize a high-value, bespoke 3D printed insoles from an idea. We will touch on benefits and applications of TPU material, how we can easily create and manipulate lattice structures for design optimization to meet functional requirements, and finally dive in to see the bespoke custom manufacturing process from 3D printing to surface finishing and coloring. Do stay tuned till the end for an amazing video that we have recorded the collaboration process between 3 companies during this pandemic period, demonstrating the possibility to collaborate remotely for design, printing, and the post-processing workflow. Before we start, I'll quickly introduce our 3 speakers of today. Firstly, we have Anikan Jain, Field Application Engineer with EOS. Anikan holds an honours degree in Material Science and Engineering from National University of Singapore. As part of EOS Additive Minds Consulting Group, he specializes in our polymer portfolio, helping customers in developing business cases through customer enablement, application consulting, and technical trainings. Anikan had led many successful polymer projects, such as the manufacturing of certified nasal swabs in Australia, and also the digital production setup for a customer in custom insoles. He will share his experience with TPU material and some best practices in printing process. Next, we have a speaker, Fanny So from Materialise. Fanny is the medical application engineer with Materialise. She specializes in the company's medical solutions for Asia Pacific market. She has worked in the medical field among major brands like Medtronic. With an honours degree in biomedical science from the University of Nottingham, along with 5 years of experience in the medical device industry, she offers her scientific expertise, training skills, and growing proficiency in customer service. Today, Fanny will share the workflow on how to optimize design for custom insoles with Materialise software. Finally, we have Jonas Koopman, application consultant with DyeMansion. Jonas started his journey in additive manufacturing at the Technical University of Munich and 2AM Research Institutes as part of his mechanical engineering master's degree, where he worked on advanced process monitoring and optimization strategies for powder bed fusion technologies. At DyeMansion, Jonas is driven to bring 3D printed products of all industries to our everyday life. As an application consultant and expert in post-processing technologies, he supports customers worldwide to unlock full potential of AM for their production and businesses. So today, Jonas will share the workflow and best practices in post-processing of TPU insoles. So without further ado, I will hand over to Anikan to kickstart the sharing on the benefits of TPU material and why it's best fit for custom insoles. Over to you, Anikan.
Thank you, Yvonne, for the wonderful introductions. Hi, everyone. Good afternoon, good morning, and good evening to all our participants from wherever you're joining. So as we start into our webinar today, let me first introduce to you the material that is in question today, and that is TPU 1301 from EOS. We will go over the why, the product examples to show that it's a reality, and introduce you a little bit to the digital foam idea. So a little bit of background about EOS is that we have a huge plethora of materials that can be chosen from for additive manufacturing, depending upon your need, your requirement, your application, and so on. And these include high performance polymers, engineering polymers, and commodity polymers as well. Our focus for today is going to be on an engineering polymer, which is a thermoplastic elastomer, EOS TPU 1301. It's a soft, flexible material. Just to give you an idea of it, TPU is a very popular material as well, and now we can additively manufacture it. So with the TPU at EOS, it is the first TPU on EOS systems with stable processing. And what we mean by this is that we tell our customers our target is actually for serial production, to have manufacturing at a large scale for TPU. So our machines, along with this TPU process, you can go day in, day out, manufacturing your insoles or whatever product you're doing, and expect a stable process over there. With the introduction of TPU, a whole new range of applications have now been possible, including insoles, and we are going to go over some of these examples of applications in a short while. Finally, and also another thing is that with TPU, various different finishes for the final product is possible, whether that is the regular finish or the VaporFuse finish, which would be elaborated more by our partners at DyeMansion for post-processing. TPU also offers us a very low cost per part because of its very low refresh rate, and it makes it extremely competitive with the traditional foams. And this is very important for our customers from a commercial point of view. Moving on, let me tell a little bit more about TPU and why it is better than our traditional foam, for example. So traditional foams like EPS, they are usually composed of several pieces. And these boundaries between several pieces are often the points of failure. But with additive manufacturing, the entire piece can be printed as a single monolithic piece, eliminating these foam interfaces and improving the safety of your parts. Let's come to comfort and performance. So when we talk about foams, they generally have linear compression, which limits the design considerably. And while the the foams with non-linear compression, they usually have a very close cell structure. As a result, it ends up trapping a lot of heat. With digital foam, a wider stress strain band can be formed, and it allows for increased comfort, allows the pressure to be alleviated in insoles, and pain to be relieved as well. And similarly, when we come to performance, when we talk about traditional foams like, let's say, EVA, they are usually limited to one or two structures when we talk about injection molding. But with digital foam and 3D printing, the freedom of design, the part can contain multiple unique zones, and each zone can have a different mechanical property tuned separately to the customer's or the patient's requirement, offering you improved lightweighting as well as compression response performance to improve on your performance overall. So within the same part, there can be different sections in which the compression force, the kind of crushability can be different as per each patient's requirement. For example, some patients, they put a little bit more weight on their heel as compared to their arch or their front section of their paw, and that within the same insole, it can be tuned to differently meet those requirements. With additive manufacturing of TPU and 3D printed insoles, all these three advantages are uniquely possible at the same time with additive manufacturing. So why is there a need for this in the market? Clearly, we have seen a rise of market fashion and trends, the demand for customization. There is a fluctuating seasonal demand, so you can, with additive manufacturing, you can respond to the demand as per the requirement. There is a lesser need to maintain the inventory and fastest time to the market that is possible. At the same time, there is a need for sustainability, and one of the pain points that our customers often face is environmental pollution. But TPU is 100% recyclable, and at the same time, when you use TPU in the print bed as well, you use the old used powder as well. So there are a lot of points in which we are a lot more sustainable towards the environment as well. Finally, with the variants, a huge plethora of variants required in the market for the customers, for the final product, additive manufacturing clearly hits that right sweet spot to resolve all these pain points for our customers. So let me show some examples that are already there in the market. Under Armour, they started printing their bottom part of their shoes for with our TPU and additive manufacturing, and using additive manufacturing, and they had they increased the performance of their shoes by maximizing the energy return that the users got, at the same time decreasing the weight. Next, we come to comfort, in which one of our customers, Atrix, they are printing insoles, and what they do is they map the entire pressure points of the customer, and as per their walking style and things like that, they make the customized insole and then send it over to their end users. And they have replaced polyurethane in this process as well. At the same time, TPU also offers protection, replacing our traditional foams, as I mentioned, because of the absence of cell structure cell boundaries or the part boundaries. The safety is much higher. So Hexar is one of our customers as well. Let me tell you a little bit more about the digital foam, that how with the advent and the introduction of digital foam in TPU, we are able to have quick iterations. We are able to have digital manufacturing. We can do simulations for the performance and the cost, and have the freedom of design to save on, and finally have the freedom of design for the various designs, and also save on the tooling costs as well for the final product. To tell you a little bit more about these, about digital manufacturing, the quick iterations or the performance simulation, I'm going to pass it over to our partners at Materialise. Fanny, over to you.
Thanks, Anikan. Hi, everyone. I'm Fanny. A big thank you for joining us. I will kickstart the process of our 3D printed insoles as Materialise by covering the software and design segment of the workflow. So we'll start off with a short intro. For the past 30 years, we've been innovating and creating competitive advantage for businesses across these three segments. So software, manufacturing, and medical. And with these three, we form the backbone of 3D printing technology. Materialise software provides companies with a platform of software tools that manage and control the 3D printing process more efficiently. And with a proven track record, Materialise software is the industry standard for 3D printing, allowing you to meet the highest standards of the most demanding industries. As an open software platform for 3D printing, we link all kinds of applications to all kinds of technologies. And this is made possible alongside our printing partners like EOS. The manufacturing arm now constitutes of Europe's largest single-site factory for 3D printing. And also here is our star for today, the TPU material. As for Materialise Medical and being a part of it myself, it includes both software and manufacturing made applicable in the medical field. The Mimics Innovation Suite, which we'll be using today, is comprised of Mimics and 3Matic. The toolbox allows you to import medical image data and convert them into 3D models. And these models will serve as starting points for a wide scope of applications, depending on what you're working on, from advanced 3D analysis, finite element meshing, personalized device design, with or without 3D printing. And for our insole, we're utilizing part of this software toolbox for design and export. Materialise 3Matic is useful in post-processing your files, fixing, cleaning, and designing. And that also includes the scope of creating lattice structures where you can add porosity to your designs, either following the contours of a surface or filling a volume. And the insoles that you see here, we'll discuss a bit more about them afterwards. So porous structures are inspired by nature, as you can see from the cross-section of the bone. It's how we're naturally and optimally built. the benefits of these hybrid or porous structures have been shared in the earlier presentation by Anniken. So I'll jump in to talk a little bit about the insoles from earlier on. Fits, they're dynamic insoles powered with Materialise solutions. Prior to our partnership, the company had several obstacles, some which are probably not new to some of you here, especially in reproducibility and possibilities of scaling up your business and production. Now we have an entirely digitalized supply chain from scan to print, with the process happening fully in-house and leading to soles that are more efficient, durable, cost-effective, along with the other notable advantages. Here's just an overview of the workflow that's in place, starting with gate analysis systems, software, manufacturing, and then your end product. Thus, there's added value in ensuring product relevance with lighter, more durable, and consistent quality. Life relevance, now more popular than ever, a personalized and patient-centric approach that are better suited to specific activities. Lastly, staying relevant in the industry with digitalized processes, minimal waste, simplified recreation, and more. Let's now dive into our prototype today. So to create the insole that you see here, I started off with a generic insole template. Most times we see the use of 3D scanning and pressure mats to allow for further personalization, as we saw earlier with fits. And a small disclaimer that this prototype was not explicitly designed to be functional, but more as a proof of concept. Okay, so the template file that I use has been prepped for design within 3matic. And by working directly on the STL file format, I already have my file in the 3D printing format and can visualize the triangles that make up the part, as you see here. So basic remeshing was done so that the file has more consistent triangulation. And I've also added a basic curved area for the heel, which you can see in comparison with the original template. And I've indicated two volumes as well, one on the heel and another on the arch, where I plan to fill with lattice. And we already defined the volume. So this is just a brief workflow on how to create the lattices. So the volume has been defined, and we will now create a graph-based lattice. So working on a graph level has many advantages. They're easy to manipulate and have small file sizes, sometimes hundreds of times smaller than when we're using actual STL files within the software. And they can also be sent directly to the 3D printing build, and also additional benefits like being able to filter them to keep the ones that are buildable and can be connected and more. So we'll see this within the software in a short 5-minute video right about now. From where we left off, you can see the defined volumes earlier, and this is the unit cell graph that we're using to fill the volumes. So you can see that it's a wire frame, and I've created this using the prism. And also there is a library for you to choose from if you don't want to create your own. So it's important for us to have a conformal surface so that we maintain a smooth top surface for the foot. And the UV map will be used to create this conformal lattice structure. Conformal lattice surface. Okay, so this is our heel. And here I'm creating the UV map. So it allows the user to place graphs or STL objects onto an unfolded surface. So just need to make sure that we have the UV maps on the top and bottom before going in with the lattice. Okay, so I'll be selecting dual surface conformal, both the UV maps. My graph, and then after applying, the results will look something like this. And we're still on the graph level with no thickness. So as you can see here, it's still made up of these wire frames. So putting that on hold, we would also create a similar conformal lattice for the arch volume. Okay. And unlike the first lattice, we're going to assign thickness to the graphs with linear gradient for this second lattice for the arch. Okay, so I'm determining the direction of the gradient here to set it to have it thicker laterally towards the edge. And it's also not strictly linear throughout and can be adjusted as shown. So I hope it's obvious on the screen on the thickness of the beams. And lastly, we can convert the graphs to an STL for printing. So in contrast with the graph, it's now a mesh consisting of thousands of triangles. I'll just toggle that. Okay. Or I can also send the graph directly through the build processor to avoid generating large STL files. So since this is relatively simple, that's okay. And after I've united all the parts together, I can do a quick label. And then a quick quality check before we export. So now when the file has been exported, then I can proceed with the downstream applications. So to wrap up, we've seen a sneak peek of design optimization with lattice structures in 3D. The final insole was then sent to Anniken over at EOS, who will now take over from me to continue the printing process of this insole. Thank you.
Hi, Fanny. Thank you for the wonderful explanation of how our initial part is created. AM process is a whole journey, and it starts with the conception of the part all the way to the finished end product. And once your initial part design is finalized, like how Fanny showed us, next comes the additive manufacturing process. So I'm going to take you a little bit more deeper into the additive manufacturing process, the steps, and move further on from there, and the success factors that EOS can help you with. So the data, how the process sequence for the manufacturing process goes is once you have your final CAD file, you prepare that data, you set it up, you orient it in various ways, then you set up you send the data to the machine. Once the data is sent to the machine, it will start the building process, after which once the parts are completed, they would be taken out, and finally the powder would be recycled and your parts can go on to your post-processing. So just to go a little bit more into the data preparation process, I'm going to show it over to you in a video that how once finally Fanny has sent me the part, I then use this part to basically orient it and position it using Materialise magics. Oh no, sorry, the video did not start. What is 2021 without any technical issues? Just a second, let me try it. Yeah, perfect. So yeah, so this shows how the part is basically oriented inside the build platform, and then we slice the data, and then that sliced data is finally sent over to the machine, and all can be done digitally. Let's go and talk a little bit more about the polymer, the machines itself, the polymer laser sinterings with EOS. Our focus for today is going to be P110 bill losses, P396 and P770. These are the machines that offer the TPU material, and depending upon your requirement, your production quantity, and even your budget and everything, your economics, we can then suggest the best material for your the best machine for your facility. Rest assured, all three systems, they produce equally good parts with properties, and there are detailed material data sheets for the systems as well. And this then, once the parts are printed from the machine, you then need to use the peripheral equipment to basically take out the parts. And we at EOS, we have a range of these peripheral equipment depending upon your requirement, your facility requirements. There is the manual solution, which is extremely cost attractive and ideal for developing environments for upcoming customers. Then we have the standard solution, which also offers a very good price to performance ratio. It is also better for the health of the operators as well as the environment, and it is semi-automated or partially automated. To show the advanced solution, I have another short video here for you. As you see over here, the entire powder management processing is automated, and it is very ergonomic and requires minimal manual requirement. This is soon going to be available for TPU as well, and it also allows for the best environment conditions, health conditions, as well as the best and the constant quality of the powder. So yeah. So far, we've seen that how EOS Materialise with its partners, they in the process of the printing of the insoles, they can assist you with the engineering complexity, whether that is the materials, the design, or the process. But printing insoles with TPU and additively manufacturing them also allows you to have greater cost performance as well. Not only do you have a better product, as we discussed earlier, in terms of comfort, performance, and even safety, it is also competitive to the traditional foams or the products that we have. So you clearly have a much better product. And at the same time, we have the supply chain. We help you with the optimizing of the supply chain with the entire digital supply chain introduction to Industry 4.0 to make sure that you choose the best facility, reduce the cost, and have the best part with you. And as we go on to help you choose with the best, to realize your end product, to choose the best finish that you can have for your parts as well. I'm going to now pass it over to Jonas from DyeMansion to take us a little bit more deeper into the post-processing process of the insoles. Thank you, everyone, and over to you, Jonas.
Yeah, thanks, Anikan, for your explanations on the printing side, and yeah, of course, for sending over these perfectly printed insoles to me. So, hello from my side. I'm Jonas, and I'm an application consultant with DyeMansion. And today, I want to show you the final step of our AM workflow of our insole, and that's the finishing step. So, what is finishing? Why do we need it? And why is it worth putting some thoughts into it? So if you look at the part as it comes out of Anikan's printer, it's basically a raw part. So post-processing now gives you the chance to adapt and to enhance the functional properties as well as the aesthetic appearance of the part. And in the end, both is needed to create a high-value end customer product that meets all the requirements of the final application. And here at DyeMansion, we focused very much on these very complex challenges that come with finishing, and today we consider ourselves the global leader in post-processing of additively manufactured parts. And that's because we offer a full industrial end-to-end workflow. And emphasis here is really on industrial. So what that means, I want to show you in the following. So yeah, let's have a closer look into it. The post-processing phase itself consists out of 3 steps. They all build up and interact on each other. So we have cleaning, surfacing, and coloring. And that's what we call the end-to-end workflow, from the print to the product. And as you can see, there are 2 possible finishing pathways DyeMansion offers. For both, the first step, of course, is cleaning. Here, the remaining powder of the powder cake is to be removed from the part to enable further post-processing steps. And this takes us to surfacing. Here, DyeMansion offers these 2 options. The choice depends on your material and, of course, of your desired surface properties. So first, you have polyshot surfacing, and that's a mechanical and non-abrasive process that reduces surface roughness and delivers a matte, glossy finish to your parts. This is done by shooting plastic beads onto the part, which level out surface inhomogeneities. However, this process you can only use for hard materials like PA12 or PA11, but it's not applicable to flexible materials like our TPU we want to look at today. So here the second option of surfacing comes into play, and we call it VaporFuse surfacing. It's a vapor-based process that creates injection molding-like surfaces. This process can handle both hard and flexible materials, so it's perfectly suited for TPU. And after cleaning the right surface structure and properties, after creating the right surface structure and properties, the last step is coloring. And these are the processes in a quick overview, but there are no processes without machines. And to better understand what's behind each step, let's have a quick look at the hardware platform. For each process, special equipment was developed with focus on automation, productivity, and economics. And this is really to enable an industrial additive production. So let's go through it quickly from left to right. First, we have the PowerShot C for the polyshot cleaning process. Then next to it, we have the PowerShot S for mechanical surfacing. That's the machine we won't consider today because it's only suitable for hard materials. And then next to it, we have the PowerFuse S for VaporFuse surfacing, where our main focus will lie today. And to the right, you see the DM60 for the deep dye coloring process. So today it's about 3 of these machines and processes, and now we want to have a closer look into each of these single steps and how it affects our application, the insole. Starting with the cleaning. Some key facts about the machine. The PowerShot C is a blasting machine specifically engineered for an automated and gentle depowdering of AM parts. It offers ergonomic operation and fast process cycles of about 10 minutes. But how does it affect our insole? And what features make this machine and the process so crucial to the success of post-processing? It's important to understand that it is not just a simple conventional blasting process. So polyshot cleaning is a proprietary cleaning process with plastic blasting media that we developed specifically for powder bed technologies. It enables higher blasting pressures than conventional glass media without damaging the parts. This higher pressure is highly beneficial if you have complex geometries like lattices. And it makes it also easier to depowder flexible materials like TPU. So it's perfectly suited for our application. The process also avoids fragmentation of blasting media that could get stuck into the surface. And a residual-free cleaning process here is really crucial for both the following surface and coloring steps. And with that, let's go to the surfacing step. With the perfectly depowdered part, we go into the PowerFuse S. And this steps really adds the functionality and the aesthetics to the part that are needed. This is a vapor-based process, so special focus here is on sustainability. The PowerFuse fulfills all health and safety standards and uses an eco-friendly solvent for smoothing. This process creates sealed and smooth surfaces as known from injection molding. And with automatic loading and unloading, you can use the machine 24/7. Process cycles are around 40 minutes to 2 hours, and that really depends on your material and your settings. This machine needs some further explanation, so let's have a quick look how it works. First, you hang the parts into a basket. So you see on the picture here. In our case, I fitted 10 insoles, but a full basket can hold up to 20 insoles roughly. This basket gets pulled into the machine and into the process chamber automatically. And you can see it later on in our video we will show at the end of our webinar. When the parts are into the process chamber, a vacuum is applied in the chamber, and then the solvent vapor can be introduced into the chamber. Due to the vacuum, the vapor flushes the complete empty space and accesses even the hidden areas of very complex part features. After that, the vacuum is reapplied to remove the solvent from the part surface. The solvent is fully recovered in the machine and can be used again and again. So it's a closed circle. The process itself is highly adjustable. You can choose between different programs to achieve your desired smoothness level. And as the comparison before and after shows, the surface is sealed and smooth. With TPU, thin structures get translucent, like in the front of the insole or in the lattice structures. Due to the vacuum, the smoothing is geometrically independent, and the lattice structures are smoothed homogeneously throughout the whole part. With this, a couple of advantages come that are necessary for an application like our insole. So first, it's more resistant to dirt and bacteria, which is really important for a consumer's part. The lattice resistance against abrasion is highly increased, and same applies for mechanical properties due to a highly reduced notch effect. Especially the thin lattice structures benefit from this effect as they have a high ratio of surface area to volume. So this you can already feel when pushing the lattice structures by hand or bending the insole. This directly shows the value of smoothing. And at last, the process keeps high accuracy of the printed part because no material is added or removed. So the outer surface layer is just being rearranged by this process. And after achieving the proper surface quality, we come to the last processing step, the coloring that gives the insole the final aesthetics. With the industrial dyeing solution DM60, a limitless color choice is offered. The process is developed for industrial production like all other DyeMansion processes. It is reproducible and automated with a cycle time of about 2.5 hours. The process makes it possible to apply a homogeneous coloring throughout the part, even with complex geometries like our lattice. In this case, we dyed the insole in black. As all other DyeMansion processes, it's geometrically neutral because the color is penetrating the part surface and there is no added paint layer on top of the surface. This has also the advantage of an increased scratch resistance, because the color is not just laying on top of the part, but is really in the part's surface. So with coloring, the last step of processing is completed. We covered the full workflow of our insole, from design to build and to the different finishing steps. So, last slide. So hope you enjoyed the journey of our insole and how 3D printed products become part of our everyday life. And with this vision of us, let me hand back to Yvonne.
Thank you, Jonas. Thank you, Fanny and Anikan, for the sharing. So now let's look at the complete digital workflow video that recorded the collaboration process of the 3 speakers within these 2 months. We started with an idea 2 months ago, and we are very happy that 2 months later, with remote collaboration, we have recorded the collaboration process on a video to share with you guys. Okay, now we are open for the Q&A session. So we have received an overwhelming list of questions. Please do bear with me as I go through the question one by one for each speaker. So I think probably I'll start with the design portion. Maybe the first question I'd like to address is from Amelia to Fanny on what is the lattice inclusion that can be included with a gradient of thickness for the beam?
Hi, Amelia. Yeah, first of all, thank you for the question. So from what I understand, is your question to be able to include the gradient that we set, the gradient thickness that we set into the lattice. So if so, then that is possible, which we've also briefly seen in the quick video earlier. But of course, if this is not your question, this was not what you meant, yeah, we can get in touch with you afterwards. Yeah. Back to you, Yvonne.
Okay, sorry, there's a very long question. Let me pull down. Okay, so there's a question from Peter. With mass customization, having such a manual process for data preparation and design processing seems like it will be the biggest cost and hurdle to scalability. Do you have any tools like NTOP or NetFab to fully automate the design and preparation process?
Yes, thank you, Peter, for this question. So yes, ideally mass customization is what the ideal goal is at the end. So the process shown is just to have an overview of what the workflow could be like and also all the aspects that can be customized and manipulated. So before we think about automation and also to script things, we kind of need to define the workflow first. So that's kind of what we are showing here in this very short webinar. So afterwards, once you have a set workflow and then you're ready to scale up, and then that's where we can include scripting. So that's where you can code the processes that you do within the software. And then that's just one aspect of it. So if you would like to go even further, you can even also come up with like something like a personalized high QT kind of interface to be able to have a more simplified process when we have to deal with high levels of high volumes of cases. Yeah, I hope that answers your question. And otherwise, there is a survey at the end. So please let us know so that we can get in touch with you and yeah, help you discuss a bit further.
Okay, one more question for Fanny. Is there any advice on what parameters need to be set in Trimatic to create the lattice structures?
Yeah, so it highly depends on what you want to achieve, and it will need to go hand in hand with the material used, the printing, and also the finishing. So in this example, myself, Anikan, and Jonas, we've had several discussions and revisions to kind of optimize and finalize the insole that we want to create for this. Yep.
Okay, thank you, Fanny. So I think probably I'll move on to the next question for the printing process, maybe for Anikan. We have a question from Peter again. TPU is also now available for FFF, filament-based technology, and MJF. What are some of the benefits of printing TPU on SLS machines?
So thank you for the question, Peter. I think first we need to differentiate FFF and MJF and SLS. MJF and SLS, these are powder-based technologies, as powder bed-based technologies as compared to filament-fused fabrication, FFF. But basically, so as compared to FFF and powder-based powder bed technologies, your resolution in SLS or MJF is significantly better when we compare with FFF. You don't see the lines between the different layers of the additive manufacturing at all. I mean, the products, the end products are comparable to injection molded products, for example. And when it comes to MJF and SLS, I mean, they are the same technologies using powder bed fusion technologies. But SLS, we realized when we did CT scans for our parts from SLS, we found out that our TPU had a much more consistent density, for example. And the second advantage that we had with our SLS machines is that as we target industrial manufacturing, you can go in and day out and have a reliable process in place. So it is that stability of the process that are clear, and the resolution with SLS that gives the clear advantages over FFF and MJF. Thank you, Peter. I hope that answers your question.
Okay, so we have another question here. Is a TPU safe for skin contact?
So yeah, basically TPU we do have the certification for the skin irritation. When it comes to biocompatibility, it's a different ballgame altogether. For biocompatibility, you need 3 certifications to be qualified as biocompatible. Our TPU has already gotten 2 for the skin irritation as well as the cytotoxicity, and we are awaiting on the 3rd results. Hopefully they will be out soon. The parts are gone for the testing. As this is a new material and I mean relatively new material as well as a new process, we're still in the process of doing it. But for skin irritation, skin contact, yes, it is safe for skin contact.
Okay, so there's really a lot of questions. I think for the questions, most of the questions with regards to cost per part, which requires further discussion, we will follow up after the webinar. And I think there's a question here that asks, what kind of outputs in terms of number of parts can the machine deliver, and is it possible to increase the print speed?
Yes, absolutely. So the numbers, firstly, they depend upon your design itself, because it depends on how many parts you're able to nest inside. Depending upon your requirement, we obviously have the bigger platforms as well, like the P770, if your output's a lot. If it's slightly lesser, maybe your P396. And for example, one of our customers, they target around 5,000 insoles, an already existing customer who are targeting around 5,000 insoles per annum, pairs of insoles per annum. Well, yeah, it can go higher as well. And the print speed can also be changed as well for TPU. With EOS SLS machines, you have the option for parameter editing, in which you can, for example, customize the laser scan speed, the hatching distance, for example, between two different exposures. And if, let's say, one customer does not have such a high requirement for surface finish, I mean, naturally, EOS's default parameters are optimized for your mechanical properties, surface finish, as well as print speed. But let's say your requirement is that maybe you do not need that much of a surface finish, because let's say you're going to do a post-processing process later on. You can increase the scan speed slightly a little bit, increase your print speed, and thereby increase the output of your production as well. So that is possible with our SLS machine.
Okay, thank you, Anika, for the detailed description. Maybe now let's move on to Jonas. I think there's also quite a number of questions. I think one question for Jonas is from Paul. With the PolyShot and VaporFuse, will that affect the surface details, for example, fine resolution and the dimensions, sharp edges?
Yeah, that's a very good question, and I think that's where the DyeMansion technologies really shine. So both for the PolyShot surfacing as well as the VaporFuse surfacing. So maybe we start with the PolyShot surfacing. Maybe or most of us are familiar with the tumbling process of parts, and that's an abrasive process. So you remove material especially from the edges and the corners. And that's why we came up with PolyShot surfacing, because it doesn't remove any material from the parts. It just compacts the surface of the parts. So it shoots plastic media with high pressure onto the part, and that levels out all the ups and downs in the surface and makes it homogeneous from upskin to downskin. And this way we can conserve all the details on the part, because we are not removing powder. And if you look at VaporFuse surfacing on the vapor process, it's similar. So by smoothing the surface, we only rearrange the outer polymer molecules on the surface, and they're getting rearranged in a way that the surface energy is decreased. So yeah, it gets smoother without removing material from the part. So it's also very high geometrically occurrence, and additionally to that, you can adjust the process very well. So you can, for example, define the smoothness level you want to achieve. So let's say you have an application where you need really high smoothness, you can use a program that achieves that. But also on the other hand, if you have an application that, for example, needs higher grip or different haptics to it, you can reduce the surface smoothness if needed.
Thank you, Jonas. I think with pre-programmed functions from DyeMansion automated machine, I think repeatable, reliable reproduction of the parts of the requirement is always key. Yeah, so I think that is something that DyeMansion does really well in automating and also pre-programming per customer's requirement. So I think there's another question with regards to dyeing. What is the colored depth that we will achieve for the dye parts?
So we say in general it's about 200 microns. Yeah, in the end, it depends on the print quality, on the layer thickness, etc. But yeah, 200 microns is a good estimation, and that's increases especially the scratch resistance, yeah, quite a lot.
Okay. One more question is regarding VaporFuse. What solvent is used? Is it commercial type or in-house product?
So that's an in-house product that comes with the PowerFuse, and the customer doesn't have to worry about it at all, because he never gets in contact with this solvent. It lasts, so it's running in a closed circle, and so it's running for a month without refilling. And yeah, so it comes with the machine. You don't need to buy it somewhere. It's not a cost driver. Yeah, and about the solvent itself, so it's eco-friendly solvent, and that's what we really focused on with this machine. We also get EU funding for it because it's a green solution to industrial production, and yeah, it's a non-harmful chemical that is that we use in this machine.
Okay, well, that's great information. I think when we talk about sustainability, it's always good to know that, you know, it's a chemical solution that's not harmful to the environment.
And maybe something more to add. So it also comes with all the certifications needed for food contact, for skin contact, etc. So it's there, yeah, all certifications needed. Yeah, get in contact with us, and yeah, I will explain all the details.
Okay, so we still have a little bit of time, maybe one question for each speaker as the last question. Question to Materialise. Are there options for more organic lattice structures in the software besides the example of the insole that was shown in the video?
Yep, thank you for the question. So yes, based on what we've seen in the video, they are mostly quite geometrical lattices. So when we talk about more organic looking, it's usually more applicable in the medical setting. So yes, we do have tools for you to randomize these structures so that they're not like very uniform. And there's also this Voronoi pattern lattice that can be applied so that you can have a more organic looking mesh that can eventually and more importantly promote bone-in growth.
Okay, thank you, Fanny. So one last question to Anikan is, I think there's a question, has the insoles been tested on human subjects, and what are the markets which EOS machines are already printing insoles?
So thank you for the question. Yes, the simple answer is we do already have our products out there. There are our customers who are sending out the end product already. And the markets that our machines are printing the insoles are actually currently Australia, North America, and Europe. And hopefully we can expand it further as well with new customers and new partnerships as well. I hope that answers the question.
Okay, sure. Thank you, Anikan. And I think the last question is for Jonas. What roughness values can be achieved by smoothing? And smoothing, does it work for hard materials like PA 2200? Jonas, you're on mute.
Thanks. So the VaporFuse surfacing works for pretty much all of EOS materials. So starting with PA12, PA11, and our TPU we talked about today. And surface roughness, it depends on the ingoing surface roughness of the raw part. But in general, you can say you can go down to R values of about maybe 2. That's a good estimation. If you want to have more details on this, we published a white paper about this topic, which really goes in-depth analysis on surface roughness. And yeah, check out our website or get in contact with me. I'm happy to explain more about this topic because yeah, that's really where DyeMansion technology attacks. That's surface roughness.
Yeah, sure. Thank you, Jonas. I think we have come to the end of the Q&A. So do not worry, there's a lot of questions. We will revert to you all the questions with answers after the webinar. So thank you very much for your time, and we hope that you have gathered new inspirations and ideas for your businesses. Please do help us improve with a short survey as you exit, and please be assured that all your questions during the webinar will be followed up via email. So if you have further queries or if you would like to reach out to the speakers for detailed discussions, here are their contact details. And once again, a big thank you to our speakers, Anikan, Fanny, and Jonas for sharing the interesting workflow for the insoles.
Thank you, Yvonne.
Thank you.
Thank you.
Thank you, Yvonne.